Okay, this is a special request to go through just two questions from this October 2021 exam for the Physics Edexcel International A-Level Unit 5, which is the one that contains thermodynamics, radiation, oscillations, and cosmology. So most students in year 13 doing this syllabus will be aiming to do this exam, which is 1 hour and 45 minutes long. Yeah. This May or June. It'll probably be in early June. Okay, so we're only going to go through question 13 and 16. So here is the second half of question 13, and here is the first half. So this is, I haven't got, due to shortage of time, I haven't got time to go through the whole paper. So I'm just going through question 13 because it was a special request. So the first bit I don't think is such a problem. Thorium is an unstable isotope that decays into radium as shown in these equations. So thorium 228 with 90 protons decays by alpha, so it loses 4 nucleons, 2 of them are protons, so it gives you radium, which is 88 protons, and the rest 224 total number of nucleons. So remember, the top number revision wise is the mass and the bottom number is a charge. Okay, so the table gives the masses of the nuclei. So thorium has a 228 mass units and it's given to 5 decimal places. When you're doing these kind of analysis where you have to use E equals mc squared, the mass defect is what we're looking for. We have to have the mass as accurate as possible, because basically what happens in nuclear reactions is that the mass on the left hand side is not equal exactly to the mass on the right hand side. Yeah, in other words, mass can be lost, and if you lose mass, then if the mass decreases, then that means energy is going to be released into other forms. So if you lost some mass, yeah, the lost mass becomes energy in a different form. Okay, so mass is just another form of energy in nuclear physics. So we're looking at thorium is 228 roughly with the extra detail. Radium is about 224. Yeah, so you can see this is the number to one integer, and this is the accurate mass when you go to 5 decimal places. Okay, and alpha is, if you add up the mass exactly, if you have the mass exactly, it's 4.00260. So when we're doing this, they want you to show that the energy released in this nuclear decay process, the energy released is about 5.5 mega electron volts. So squiggly line because it's about. Okay, so we want to see that. So we've got to use E equals mass defect, which is delta M, times the speed of light squared. So the mass before minus the mass after in units is what we want to do. So the mass before is obviously just the thorium, which is 228, and the mass after is about 228 as well. But when you actually do it to accurate number of decimal places for the units, you'll see that there is a 5.92 times 10 to the minus 3 units missing. Okay, so there's a decrease in mass. Okay, so this energy has gone into other forms. So to be able to get how much energy that is, you've got to change the units into kilograms. Now 1 unit is this number, and that's on the data sheet. So at the back of the exam they've provided this data. So you need to know that 1 unit is always 1.66 times 10 to the minus 27 kilograms. So that's the amount of kilograms per unit, and we've got a fraction of a unit, about 1,000, 6,000th of a unit. So when you work it out in kilograms, that's your second marking point, 1 marking point, 2 marking points. Then you have to, so once you've got it in kilograms, you can then use E equals mc squared. So here is where you do E is delta M times c squared. It gives you the energy in joules. Once you do this, you can get the energy in joules. Okay? And once you do that, here's the mass in kilograms multiplied by the speed of light squared. You'll then get the energy in joules. And once you know the energy in joules, by dividing, this equation is actually using E equals QV where the energy in joules shows you the equivalent electron volts, which is this value, and the constant proportionality between them is the electron charge. Okay, so this is 1.6 times 10 to the minus 19, so that's also on your data sheet. Once you do that, you can see that when you change it to, just need to move the paper slightly so you can see what I'm doing. So just to reiterate this point, so you divide the energy we worked out in joules by the charge of one electron, so the charge of this case, so that's how you get electron volts. This is basically the energy an electron would gain if accelerated by a certain voltage. Okay, so this, if we talk about the other way, the amount of joules is the amount of voltage in electron volts. So you could, it's basically equivalent to accelerating an electron through 5.53 megavolts. Okay, so that's approximately 5.5, yeah, to two significant figures. It is 5.5, which is what they asked us to prove, to show in the question. So that's the first part of question 13. I don't think most people would struggle with that. The second part then is looking in a bit more detail at some algebra that you need to do. It states a textbook. It says a textbook states that the kinetic energy gained by the alpha particle when a nucleus of thorium decays, yes, which is what we just looked at, is equal to 5.4 megaelectron volts. And remember the value we just worked out in the first part was, the amount we worked out accurately is 5.53 megaelectron volts. Okay, so that's the accurate value. So so compared to 5.53 megaelectron volts, which actually is the energy released. Yeah, so that's the energy released. 5.53 megaelectron volt is the energy released in the decay. And the textbook says that the kinetic energy part of this energy, the kinetic energy gained by the alpha particle, is 5.4. So most of that energy basically becomes the kinetic energy of the alpha particle. Okay, so it's nearly all of it, but it's not quite all of it. So you have to comment on the statement. Your answer should include a calculation. Well, actually, the calculation is not a simple calculation. I think if you want to answer this question fully, as I have, you need to make sure you do the maths clearly so people can follow it. So I've done it in detail. When alpha decay occurs, the emitted alpha particle gains momentum in one direction, say forwards. Yeah. So if the alpha particle, so here's your original nucleus before, yeah, it's stationary, so that would be thorium. So afterwards, what happens is the alpha particle comes out that way. That's the unit, 4 mass units, and therefore the thorium, which then becomes the radium, will recoil. Okay, so the amount of momentum in one direction must equal the momentum in the other direction. So if we're looking at momentum, the momentum must be balanced. So the nucleus recoils backwards, in other words. So if we say the alpha goes forwards, then the nucleus recoils backwards, obviously, due to the conservation of momentum. And that means, mathematically, the sum of the momentum before was 0, so the sum of the momentum after was 0. So if alpha particles are positive, so positive momentum alpha will equal the negative momentum of the nucleus. Okay, so they will get 1 mark for understanding the conservation of momentum as the main principle. Then you go on to explain, well, you need to know the ratio of the masses. So the ratio of masses, obviously this is important to 0 decimal places. So we're just talking about roughly 224 to 4. We're not going into the 5 decimal places we used before for E equals mc squared, because it's not going to be significantly different to 224 to 4, which I think is actually a ratio of 56 to 1. Okay, so in other words, the radium is 56 times more massive than the alpha particle. So that means if the mass of the radium atom nucleus is 56 times the mass of the alpha particle, that means the velocity of the alpha particle will be 56 times greater than the velocity of the radium nucleus recoiling. Okay, so this one's going to have a small velocity and this one will have a large velocity. Okay, so you could say velocity of alpha will be 56 times the velocity of the nucleus. Okay, now we don't actually need to know that, but it's interesting just so you understand the underlying concept. The total energy released, 5.53 megaelectron volts, becomes the kinetic energy of the alpha particle and the kinetic energy, of the nucleus. Okay, so this is the energy conservation. So from part A we know the 5.53, and this is an energy conservation principle. So first you're talking about the conservation of momentum, now we're talking about the conservation of energy. So we know the total energy must add up to that, and we know the mass ratios, and we also know the velocity ratios. But how do you work this out algebraically? Since we know that the positive alpha momentum must be equal to the negative momentum of the nucleus, you can actually use this. So you know that from the equation sheet, kinetic energy is p squared over 2m. If you don't know this equation, it's kind of a useful one to look at. It's on the data sheet. It's on the formula sheet. So if you change it, you can now put p equals the square root of 2m over ek. So that's just algebra. So if you can do that, then obviously the alpha will be twice the mass of the alpha times the energy of the alpha, the kinetic energy this is. Okay, so both of these are kinetic energy. Yeah, when we're talking about these, we're talking about all kinetic energy. So basically the mass the energy that's released from the mass, 5.5 megaelectron volts, becomes the kinetic energy of the recoil and the kinetic energy of the alpha particle. Okay, so this will be under the square root sign, so you just put the values in for the alpha particle. Twice the mass of the alpha particle times the kinetic energy of the alpha particle must equal to the negative value of twice the mass of the nucleus times the energy of the nucleus. Okay? And if you just looked at the mark scheme, they haven't explained this part. They've just gone straight into the maths. You square both sides, it gets rid of the negative sign. Therefore, this must be true too. Okay, so you can square both sides. Yeah? All right, so if we do that, that would be true. So once you do that, you know that the energy of the alpha particle, if you change this, so basically you got rid of the square root signs. So you know the 2's cancel out, and then you got the mass of each one on each side, the energy of each one on each side, and so in other words, the mass times the energy should be equivalent of the both sides. Okay, so if we do that, we find that the energy of the alpha particle, by changing the subject formula, because remember, this is what we want to work out. We want to work out the kinetic energy of the alpha particle. So you make the kinetic energy of the alpha particle. Remember, all these energies are kinetic. Okay, is the ratio of the masses, which we've already worked out is 56 to 1. Multiplied by the energy of the nucleus, okay? And we can substitute for the energy of the nucleus using this equation, okay? Once you do that, you've only got one unknown, which is the energy of the alpha, because you put the 5.53 minus the energy of the alpha in there, and you put the numbers in. There's your 56 ratio, 224 to 1. 5.53 is the total energy. Take away the energy, expand that brackets, and you'll see that's 56 outside the brackets, 5.53 minus the energy of the alpha particle. Okay, so you simplify this, 56 of these. If you put them on the other side, you get 57 in total because you've got one this side. Okay, do the algebra, comes out to 56 times 5.53, comes to this number. You then divide it by 57, you get 5.43 megaelectron volts, which is approximately 5.4 megaelectron volts, which proves what we were set out to prove. Okay, so that's question 13. The next question I was asked to do was question 16. So we're going to go straight to question 16. And question 16 is about astrophysics, or is it called cosmology in this topic? Okay, so we have the diagram showing the sun is rotating. So most things in space rotate. Okay, about its axis. So the axis is here. So this side is moving that way, and side A is moving that way. And of course, the center of the sun is on the axis of rotation, so it's not really the spot which is always in front of us. So we're looking at it from the perspective of the Earth. Okay. So A, B, and C are points on the surface of the sun. Light from points A, B, and C is analyzed. The wavelength lambda alpha, It's called the alpha line in the hydrogen spectrum. So we're looking at one specific line in the alpha spectrum is determined for the light from each of the points A, B, and C. Okay? Now, what we got to do is work out which one's which. So obviously the one that's in the middle is not going to be affected by the rotation because it's basically always in the same spot, whereas this one is relative motion. It is away from the Earth. Okay, it's going that way. And this one is coming towards the Earth. So you've got a redshift, blue shift issue. So the one that's moving away from the Earth is be redshifted, so it should have the higher wavelength. So the higher wavelength must be B. Yeah, this is the center one, so it's unchanged wavelength. So this is the middle value, and this is the lower wavelength. Yeah, so it's blue shifted because at A it's moving towards us, so the wavelength will be lower. Okay, so the longer I put higher, so this is longer lambda, and this is shorter lambda, just so we don't get things confused. Okay, so we can work out which one's which. That's the first thing. We got 1 mark for working it out correctly. It then says, explain why there's a variation of the wavelength of the light from different parts of the sun. Well, light from, is basically what I've explained here, so you've got to put it in English. Light from B is redshifted towards larger wavelengths or longer wavelengths, as its rotational motion makes that position or side of the sun move away from us on Earth as relative velocity. Okay, so therefore it would produce redshift. Okay, so redshifted, larger wavelengths, and that's the next mark. And then you do the opposite for the light from A is blue shifted, as its rotational motion relative to the Earth is towards the Earth, which makes the wavelength slightly shorter. So, okay, so longer and shorter. There's your 3 marks. And then part C, which is possibly the part where the request for this question to be done was made. In the laboratory, the wavelength of the alpha line in the hydrogen spectrum is the middle value, lambda, so unchanged. I put it as lambda naught just to specifically say it's the same as the position C in part A, basically the part that's not rotating relative to the Earth. Okay, it doesn't appear to be. It is rotating, but it's going sideways. Assess whether this is consistent with the sun having a period of rotation, yeah, of approximately 28 days. Well, you could work it out in seconds, but you don't need to, okay, because they told you how much a day is in seconds, okay, 24 hours. Okay, so they're giving us a radius sun, so we got to work out the period of rotation of the Earth and see if it matches. Well, we know these equations from the equation sheet, that the velocity of the rotation, if you like, creates the shift in the wavelength, and the ratio of the velocity of the relative motion compared to speed of light is the same as the change in the wavelength divided by the original wavelength, which is the value here, which is the same as the part which is not in relative motion. Okay, so we could say this is lambda c, yeah, the wavelength at position C, which is the same as I put here. Okay, if you look at them both, they're exactly the same number. It's the same decimal places. Okay, so basically we can change the subject to the equation. We want to work out the velocity first, because once we work out the velocity, we can then work out the period using this equation. So that's the underlying path we're going down. So once you do that, we know the speed of light, we know the change in the wavelength from the table given in part A, and we take away the larger one from the smaller one, or for the position at C, the unchanged one, because this is in a lab, means it's obviously in a lab, it's not moving away from you, so it would be the same as if there's no relative motion, and divided by the same value, which is lambda naught, which is the lambda in the center position on the part A. Once you do that, you get the velocity. Okay, so you get a mark presumably for that. You'll probably get a mark for different parts of it. I can't remember what you get marks for. One for using this equation, basically. One for getting the numbers, maybe. Okay. One for using this equation. So you're getting the value out. So I think maybe you'll get one for all this. I'm not sure. You'll get one for that. One for working it out to calculate t. And one for changing it into seconds by dividing it here. Okay, so we know how many seconds it is. We know that 1 day is that many seconds. Divided by the number of seconds in a day, you'll get us about 27.8 days, which is approximately 28 days. So this is for one of my students who asked for me to go through this. We are doing our first mock this week, so this is just to help them prepare for their mock exam. The exam, we still have time to get ready for the Unit 5. So I hope you found this useful. Anyone else watching this? Unfortunately, I won't probably have time to do the rest of this paper, but there will be other Unit 5 papers coming on. As I do the mocks, I'll probably do the ones which we use as the mocks, which will be the most recent papers. Okay, so if you found this useful, please like, share the video with any friends that you have doing the same exam, and please subscribe so you'll be notified when the next video is ready. And I hope you're also watching my Uma the cat videos, just to keep things a little bit more relaxed in the pressures of this exam. So bye for now. Hopefully see you in the next video.